Can you try if it is moving? Okay.
Yeah,
Okay.
it looks good.
Then I guess we can get started, I assume. Should we get started? Okay, cool. So then, welcome everyone to the very first presentation of this semester's seminar course on computer architecture. Today, Severin will present this work, which is enhancing sequence alignment accelerator throughput via hardware scheduling. This work was presented, it appeared at HPCA last year in 2023. So let me also introduce Severin very quickly. He is a master's student. He is finishing actually his master's very soon, I guess this summer, hopefully.
Yeah,
he is studying in electrical engineering and specializing in computers and networks. His interests include domain-specific architectures, languages, and hardware-software co-design. His longer-term plan is to pursue a PhD degree on one of these domains. So maybe we'll see more of his works in the future as well. So
hopefully, yeah. Okay. Yeah. Thanks for the introduction, John. And yeah, I guess I don't have to go over the title anymore. But yeah, welcome to the presentation on NvWa. Yeah, so as an outline, I will first give a brief background on DNA alignment, so only the minimum what you need to understand the paper. Then I'll give the motivation that the authors had to do this work, so what weaknesses they see in previous literature on genomics processing. Then I'll go into their mechanism, NvWa, that they propose to solve these issues. Then we'll go over results, and then also, of course, the strengths and weaknesses that I think this paper has. And hopefully I can get you excited for the discussion afterwards. Yeah, so let's go over the background a bit, over genome alignment. So this is basically like a short version of what John also presented the past 2 weeks. So, but I wanted to get everyone on the same page. So basically what you want to do in genome alignment is you have this very long reference sequence that can be like over like billions of characters, and then you read these short reads from the DNA sequence, and basically the goal is to find which part of the reference this read corresponds to. And one simple or like one common algorithm to do so is this hash-based approach. What you do here is you split, instead of comparing all of the read with all of the reference, which would be very expensive, you split up this reference into these called k-mers, and then map all of these k-mers onto a hash. What is useful, you do the same with the reads, basically. You split it up into these shorter sequences and basically find these short exact matches between the read and the reference. So yeah, basically remember these are like exact matches that are like just of short length, so not our final results. What you then also do, but it's not super important to understand the paper, is filtering. So basically you leave out those matches that are like very short or maybe like not very informative. And then finally, the extension extends the short exact matches to approximate longer matches. So basically what you do is approximate string matching. Maybe you had that in your algorithms class. But basically this considers also that there could be errors between the read and the reference genome. To make this clear, like I have 2 more shorter examples. So yeah, seeding is the process of identifying these short matches between the reference and the read. So basically you have this reference and then your reads or queries, sometimes also called, and find these short potential matches. And then in the extension phase, you use typically some dynamic programming, but there have also been other automator-based approaches that extend these short reads that you have found in the first step, that extend these to longer sequences. And what you see here also, this sequence, for example, has an error. So we would have to tolerate errors because probably the reference genome is from a different human being than the reads, because yeah, otherwise the whole process wouldn't really make sense. So then maybe this person of the read has like a disease that the reference didn't have, or like just a different hair color. So that's why we need to consider errors. Otherwise, we will not find any like very long matches between the two. Okay, and yeah, for a very long time, so we've had these, or like we've had these special purpose, these sequencing machines that can produce a lot of genomics data. But for a long time, there were not really any specific architectures on the receiver side. So we had application-specific hardware on the data generation side, but not on the processing side. And of course, there's like a big imbalance here, as you can see. And then like from 2017, I think 18 on, there started to be more works on that targeted this data analysis step for genomic data. And yeah, Safari Group has also done like a multitude of works, of course, on this. And yeah, then the authors of this work see certain weaknesses that are not properly addressed in their opinion in these previous works. And yeah, that's what we will cover from now on. Yeah, so now I'll give, as I said, like why the authors came up with this work, what kind of weaknesses did they see in previous literature. So let's first, I will give a brief summary of what we'll see in the next slides. So basically the authors find that there's like an imbalance in like an irregularity in the genomic data that has to be processed. And that leads to also an imbalance in the utilization of the seeding and extension units. So I haven't really explained what these are, but basically, as the name says, they target the seeding and extension phase that I mentioned before. And ultimately, this will also reduce the throughput of the accelerator. And this, of course, is quite bad because the accelerator is only so efficient because it can have a high utilization of the units. So the goal of this work is to build an accelerator or ASIC that improves resource utilization and throughput, and they do this mainly by incorporating dynamic scheduling into the accelerator. So key contributions are three schedulers, basically. So a seeding scheduler that targets variance in the seeding process that I described, an extension scheduler that targets imbalance in the length of the hits that are found in the seeding phase, and then a coordinator to handle interaction between the two. And with this, they managed to improve throughput and reduce energy consumption compared to the accelerators and also general purpose processors that they compare to. Okay, then let's go into more detail into the challenges that the authors found in previous work and genomics processing in general. So the first one is what they call seeding termination diversity. So basically, what you do in the accelerator is like commonly you parallelize across the reads if you have shorter reads. This is feasible, and the reads are independent of another. So it is favorable to parallelize across the reads. But what you see here is if in this plot is on the x-axis are the some random reads that they profiled, and then the runtime that it takes to perform seeding and seed extension for these reads. And what you clearly see is if you just look at the seeding, but same holds for the extension, that there's like a large variance between the runtime it takes to process each of these reads. And what a lot of other previous works have done is like to batch these reads. So for example, like you would schedule for like a certain number of reads in parallel and then wait until all of them are finished. And as we'll see later, this will lead to a reduced throughput of seeding units. Then the second challenge that they find is the extension scales diversity. So this is similar, basically leads right into the challenge we just saw before. So the hits that are found in the seeding phase, so the hits are these short matches that you find from the seeding phase, for example, with this hash-based algorithm. So they also can vary strongly in length. And generally, extending these hits, these exact matches to longer sequences, that can also vary a lot in runtime depending on the hit you have. So then previous accelerators that were proposed, they had like multiple of these extension units. So if you have multiple hits, you can schedule these hits on multiple extension units. But what they had was that all of these extension units were basically homogeneous. So all of them had the same number of processing elements. But you can think like maybe if there's a large irregularity in the hits that you find, maybe it doesn't make sense to have like a homogeneity on the processor side. So again, this could lead to reduced throughput of the extension units. So yeah, briefly to maybe make this a bit more clear, like I'll go over like what an example extension unit could look like, but this is just specific to this architecture, but could also look different. So for example, if you have this query, so which resembles the hit in this case, yeah, authors used a bit misleading naming maybe, and then this reference from the seeding phase. Basically, you load these into the systolic array of processing elements and basically perform this alignment step, for example, with dynamic programming. So yeah, this is like.
Zuerst dein iPad entsperren.
I don't know. Yeah, okay, whatever, ignore this, hopefully it will stop, but okay. Yeah, basically what they do is you have to load these into this processing elements, and yeah, for now the processing elements can be like a black box. But basically what you would see is like if you have a very short query and like have a lot of processing elements, this would not be great. And you have to wait a lot of time until this whole query propagates through all of the PEs. And at the other time, if you have a very long query and only little PEs, then this will also not be great. And you have to maybe slice it up into multiple hits. Then as a third challenge, they put basically two other problems that they see into one, what they call the third challenge. So the hits fragmentation problem is basically more like a technical issue with their buffer. So basically, maybe you cannot schedule all the hits in one iteration, for example, because some of the extension units are occupied. So then you need to like basically buffer them, and maybe like they will be at an unfortunate location and then will be basically starved because they will not be reconsidered in the next step. So this is what they call the fragmentation problem. And the allocation problem is basically how to optimally assign the hits. So basically you produce hits from the seeding phase and want to consume them in the extension phase. So this is like a producer-consumer model. And you want to assign them to these extension units so that you achieve high utilization. So you don't want to have like a short hit on a huge extension unit with many, many PEs, but you also don't want any hits to starve, basically. So yeah, in short, like basically how do you assign these hits onto these extension units with a certain number of PEs? Okay, now that we've seen the challenges that the authors see in the given literature, what do they propose to solve this? So basically, they're built on top of this generic architecture with some seeding and extension units, and they don't design them themselves, but they take these units from the Darwin paper, which was like one of the first genomics accelerators from Bill Daly. And so on top of this architecture, they built a seeding scheduler to target the first challenge I mentioned, an extension scheduler to target the second challenge, and a coordinator to target the third challenge. And in the next slides, we will see what each of these boxes basically does in a bit more detail. So basically for the first challenge, they do something quite simple. So on the left, you see what is done if you do not basically do dynamic scheduling. So what you would, for example, do on the x-axis, you have like the units. So say we have 4 of these seeding units, and on the y-axis, you have the time. So basically, basically you would schedule all of these reads in the first step. And then if you do batching, so like static scheduling, you would basically have to wait until all of them are finished until you can schedule the next batch. So of course you would have a lot of idle seeding units here. And so what they basically do is they do dynamic scheduling. So every time like you see there's some idle unit, then you basically schedule another read. So basically you break up these batches essentially. Yeah, for the second challenge, so basically I mentioned that there's like this imbalance in the hit length that you get from the seeding phase. So for example, if you have this very non-uniform distribution that is like not very centered at one length, so you have a large variance in the hit lengths, it might not make sense. For example, if you have in your FPGA, you can build you have a fixed budget of 256 PEs. It might not make sense to distribute them uniformly across your processing units, but it might make more sense. And this is what they propose is like basically to split up the PEs non-uniformly, so that you get like some units that have more PEs and some with less. So basically to address this distribution, and then they give some formula that I don't really want to bother you with, but basically how to find the optimal assignment, like for a given distribution of hits for these extension units. And then finally, for solving the hits fragmentation, they keep track of the unprocessed hits that you could maybe not schedule in one iteration, and then like basically move them in the location in the buffer so that they will be reconsidered for scheduling in the next iteration. For solving the hits allocation problem, which was the second part of challenge 3, what you do here, I think the authors are not super clear here to be fair, but basically they divide the extension units into groups according to the number of PEs they have. Then they divide the hits also depending on their length. And then they try to basically assign the hits like optimally to, like they assign each group of hits to another group of extension units, and they try to allocate hits to like the most suitable extension unit. So basically assign long hits to large extension units and smaller to small ones. And if they're not available, then try to find like the second most suitable one basically. Okay, this was it for like the main architecture, main mechanism of the paper. So yeah, then let's see what results they achieve with their idea. So briefly, I'll go over the setup that they use. So they have like a Python simulator to verify the ASIC. Yeah, they wrote the Verilog, got the Verilog of their ASIC, and used this Synopsys design compiler, this commercial compiler, to evaluate the area and critical path. And they used the Cacti open source tool to find area power and latency of the on-chip memories. And as a data set, they use this like this standard genome data set of a human. Yeah, you can look this up, like, but it's like basically one of the standard, most commonly used data set in genome analysis for humans. So as baselines, they take an Intel CPU, and they take this genome processing software package from another work, and also yeah, they also compare with a GPU with an A100, and they also like use some CUDA-based software package here, and then they also compare with 3 other accelerators. So one ASIC, one processing and memory accelerator, and one FPGA. Yeah, and then they also give the specs for like the CPU, the GPU, and their accelerator. So like on-chip and off-chip memories. And yeah, like we're not at the weaknesses part yet, but like it's a bit, yeah, they use like different memory off-chip memory bandwidth. So of course this will also affect performance irrespective of what processors you will have. Yeah, so let's first look at throughput, which is of course a relevant metric to have an efficient accelerator. So yeah, first these bars here show basically all of the works that all of the processors that they compare with. And then basically, yeah, this bar shows then if you use the ASIC with the seeding and extension units without any of the scheduling that they propose. So this is like kind of what they compare with. And then from adding this with hybrid, I mean like this non-uniform assignment of PEs onto extension units, they gain a 3.3x factor. They gain another 1.7x by using the seeding scheduler. And finally, with the coordinator, so this yellow bar is like their final work. They managed to like improve over the best work that they compare with, which is the processing in memory gen cache accelerator by 2.3x. And yeah, not very surprisingly, they beat like the FPGA and the general purpose processors by a large margin. Then of course, power and energy is relevant for an accelerator because like, yeah, if you want to design a very specific architecture, and then if you put this some scheduler on your chip, then this might like have a big, if you have like, for example, a big out of order queue or something, take up a big area on your chip. But what they show basically is that still like most of the power and area is still occupied by their processing units. So this is of course what you want. You don't want the scheduler to be like a big part of your power and area. And yeah, they also improve over the compared works in terms of energy efficiency. Yeah, because they improve over throughput and power, and then yeah, basically resulting from that, you also improve over energy. One of the main selling points of the paper was like that the resource utilization in other works without dynamic scheduling wasn't great. So they also provide the results for that. So basically on the left, you see what happens if this batching approach, yeah, basically like in the beginning, your utilization is high at the beginning of each batch, but then like you are always bound by the longest lasting read in your batch. So then like the basically, yeah, your average utilization is pretty low. And with their approach, like you manage to stay quite constant in utilizations, almost 100%. But I do have to say that this on the left it's not like a previous work that they evaluate here, but like it's their accelerator removing all of the scheduling, then you get this result. So that should be set here. And similar for the extension units, that is just have some outliers that are not that important, I guess. Okay, then yeah, let's wrap up the main part of the paper. So yeah, basically what the authors found in previous literature was that there's an imbalance in the reads of a genome that you want to process. And this also leads to an imbalance in the utilization of your processors and will ultimately also lead to reduced throughput. The goal was to improve this resource utilization, ultimately throughput, by using dynamic scheduling. And key contributions are the seeding scheduler, the extension scheduler, and the coordinator that we just saw. The results are improved throughput and reduced energy consumption over the baseline that they compare with. Okay, then that was the main, were the main results of the paper. So then now we're going to strengths and weaknesses that I see with this work. So I think one strength is that it's like a quite general approach. So in principle, you could also build this on top of other accelerators. So I think one problem maybe with other accelerator papers is that they target like a quite niche problem with a quite niche idea, and then it's a bit hard to take away from this paper, like what can I take away from this for my own accelerator research. So, but what they do is like a more higher level or like general approach that could also be built on top of other accelerators. So then they pose as a goal, they say we want to improve resource utilization and throughput, and yeah, they managed to significantly improve throughput, and they're no longer bound by like batch sizes or static scheduling. Yeah, importantly, they only add little to the area and power of the ASIC. And I think it nicely combines the known concepts in computer architecture, so like dynamic scheduling, in a novel way in genomics. And yeah, it's also one of the first genomics accelerators in general to target the interaction of seeding and extension between the of the reads explicitly. Of course, this paper also has some weaknesses. So yeah, for example, they show, and other works also showed this, that the seeding phase is very memory bound, but yeah, what their scheduler is basically only targeting to improve the resource utilization of the processors. So basically, it's not really taking into account what kind of memory demands do all of the processors have. So I think maybe some more memory-aware approach for scheduling for the seeding phase could be more suited here. Yeah, they also claim that this could be transferred to other seeding and extension units, like which would make the approach, of course, particularly useful, but then they only evaluate the results for one pair or for one implementation of the seeding and extension algorithm. So they don't really back up the claims. And I think, yeah, we can maybe discuss this later also if you have ideas, but yeah, I think if the seeding and extension units change, then yeah, maybe like the whole accelerator architecture and scheduler might like need like reconsideration, I think. I also think like the performance depends a lot on the input data set. So for example, if you find if you have this hit distribution for a human and then find the optimal number of extension units per processing element for a human, and then like you want to use this accelerator on like another species or something, then maybe like the hits distribution might be completely different. So maybe, yeah, like this whole allocation of PEs to extension units might not really work that well anymore. So I think there's also some bit unclarity. So I showed before this table where they showed like what kind of off-chip memory they assume for the CPU and GPU, and they don't really. They say that there's not really data for the memory power for the accelerator, so they come up with a number, but don't really show like where this number is from. So I thought this was a bit intransparent, and also as I said, like the off-chip memories have varying bandwidths. So of course, this of the works that they compare with of the CPU and GPU. So of course, this will also have an influence on the general performance, and they will not only evaluate what the accelerator actually does, but also the memory. And then I think they nicely show that with their scheduler, they improve like the throughput over like if you use their work without the scheduler, but then for energy, like those numbers are also missing a bit. And then that's maybe not essential, but I think they could have the writing is a bit redundant, so they repeat these challenges like over and over again, like 3 times I think throughout the paper. And generally also the plots, I think they could have been improved, like for example, coloring and like some things where like were not easy to grasp, I think, directly. Okay, then I think this was like the main part. So then if you have any questions right now or want me to go over anything again, then I'll happily do so. Otherwise, if you have any points to discuss or questions, then we could go into that. I also have some discussion questions prepared, so we could, if you don't have, if you have any idea of like what could be like downsides of this dynamic scheduling approach, or what could be improved, then I'll be interested to hear that. Otherwise, we can also go over my questions. Yeah. Okay.
Can you explain the difference between the first strength that you had and one of the weaknesses with that? I couldn't understand the difference between the first strength here, that this is a general approach that you can apply to other accelerators, and the weakness listed in the next slide, which is
you mean the
unclear if the method can be transferred.
Yeah, that's a good point. So I think in general, like the approach doesn't make assumptions on the like microarchitecture of the processor. So basically, the authors claim that this is true, but what I'm basically criticizing, maybe I should have made this more clear, but that they should have evaluated it then on like 2 processing elements. If they think that it's true, then like I think their claim might be true, but they basically cannot back it up. So I think like from the idea, like I could imagine that it should work in general. There probably needs to be some tuning of like the on-chip buffers and like this allocation of PEs on the extension units. But I think it would have been nice to also use like one of the other seeding and extension algorithms and show it works with them. But yeah, exactly. Yeah. Oh, that's one more person there.
Do you know how much of those intransparencies you've talked about, not regarding the methodology, but maybe the numbers come or are inside the simulation backed up? Or do you think or is it explicitly told that they came out of thin air?
You mean, for example, like what
for the power and the bandwidth stuff?
Yeah, I think probably they just assume some kind of memory technology that should be used for the other so this was for the other accelerators, and then just take that number and maybe forgot to reference it, I guess. But like, I mean, it depends on what kind of maybe they also took a number that's like extremely high just to like make their work look better. Of course, that could also be true. I'm not sure. Like, I think it's probably that they would assume like a worst case maybe for the other work. I could imagine, if that answers the question. Oh, yeah.
Could you maybe, so you addressed that you could potentially implement it on, or they said that you can potentially implement it on other systems, but how practical would it be to do that? So do they address that somewhere? So would someone even, I mean, you said that there's a clear improvement, but is it something that's really hard to implement, or would it be worth basically to do that?
So basically, like to take this approach and like basically build it on top of your accelerator, like Oh, that's a good question. Like, I mean, I didn't look at like the code or something that they didn't write explicitly that like you could plug in your units and then just like have it finished basically. So they didn't mention anything regarding that. Yeah, I don't think they released their code, so I think it's a bit difficult for me to say. So probably what I think would need to be done, like I have one slide regarding this. So what you basically also need to do is like, again, like probably like if you, for example, use a seeding unit for like that does like another seeding algorithm. So we saw this hash-based one, but there's like the Burrow-Wheeler transform one. So if you do that, then maybe like the seeding is more like takes longer or like takes shorter time. So then probably you need to, for example, what I wrote here is like they show that like the buffer between the seeding and the extension like has a lot of influence on the utilization. So I probably need to like tune these like parameters again, like for example, find the optimal parameters again. But from the implementation side, yeah, I think it's hard to say. Like they don't mention that they have like they didn't provide a tool to make it easy for you. If that's the question, no, that's yeah.
In the area and energy breakdown,
Yeah.
the EUs consume the most amount of area and power in terms of the SRAM portion
Mhm.
of
Yeah.
like that's 21.15 mm square out of 27. Is there a reason why? And did they use an accelerator that's already there, or is this an accelerator that they built?
Yeah. These are like both from the Darwin paper. So yeah, they don't build them themselves.
Okay.
So yeah, I guess like you need a lot of like probably SRAM because you need to like process a lot of data like at the same time, I guess. Like I mean, yeah, it's true that like it's interesting that the extension units have like much more than the seeding units. But yeah, probably like because it's also very memory bound, and then it's probably favorable to have like a lot of SRAM to basically keep like the data that you're like the read that you're processing on in SRAM, for example. But this is like not their implementation, no.
Okay. One more question.
Hmm.
So you said that the work focuses on a processor-centric domain. They don't think about the memory side of things, given that seeding is memory bounded. In their motivation, do they evaluate whether the workload is memory bounded or not, or do they just motivate the fact that
like they take it, I think, from other work that it's memory bounded. So yeah, but so the scheduler doesn't really address the memory boundedness. Like it only maximizes for the processor utilization. Like they say, there's work that is more tailored for like optimizing the like memory scheduling, and you could build this on top of it. But yeah, like again, like they didn't wake up that it could work together or like wouldn't interfere or something. So yeah, I think this could be an interesting approach to maybe like optimize, I don't know, try to schedule like the reads or like they have the most memory requirement intelligently or something like this. Maybe could be interesting, yeah. Okay.
Other questions?
Yeah, if we still have time, then I still have some maybe discussion points. I think, yeah, you raised some good questions. So I think we went over quite a bit of what I had here. I think we covered this. So yeah, maybe one other question that I had prepared. So yeah, maybe like, what do you think, like if we have like the accelerator, use it for like a human, like I talked about a bit before, but what might change maybe if you have like a different species? Why would this matter? Or maybe like how could you make it like adaptive to input data, or like how could you make the accelerator maybe like recognize which species this is, or maybe like build the policy, the scheduler based on the species that it sees at the input? Or like do you have maybe ideas why this could matter, or like what could be ideas to implement this scheduling?
But wouldn't that rather depend on the distribution of your input units? Because you have to have the right distribution of input processing units. I mean, for the right distribution of your data, right? So does it change anything for the scheduling algorithm, or does it more change how many and of what size you have the processing units? If you have different data.
Yeah, I think it's. I mean, I don't really know, but I think what I thought about, like maybe if you have like a different species, then maybe I think some have like different genomic variability, and then maybe you have more or less hits, and maybe the hit distribution could also change. So yeah, you're right that this would change like the number of processing elements you would assign to the extension units. Maybe it could be that like some species have like shorter hits, for example. I mean, I'm not 100% sure, but I think it could be. And then this could also like affect the scheduling, right? If you have like maybe shorter hits, then it would be faster to do the seeding. And then maybe like it would be like there would be more pressure on the extension units, so there would be like more seeds being produced or more throughput from the seeding part. So I think maybe this could be an effect. So yeah, but they don't have any experiments on that, but I think it could be the case. And yeah, what I also thought maybe like to make it like adaptive to the species is maybe like, first of all, tune the policy based on like the species, or like there's like a lot of research maybe on like also by Safari, like on how to build these learning-based approaches for like, for example, cache replacement. Maybe you could build some like learning-based approach to like, of course, this would be like more overhead, but then like see what species we have at the input, and then have the scheduling policy basically based on that. Maybe, I'm not sure how feasible this would be, or if the overhead would kill the accelerator, but maybe this could be used. Yeah. What was my last? Yeah.
How much does it specify, or do you know how much the variance depends on the species or on the quality of the data?
Yeah, good question. I'm not 100% sure, but as I mentioned here, like what I only know is that like the variabilities of, for example, like maybe humans are more different to each other than like some animals, maybe like very practically. So the DNA might also be more similar, and there might be more matches in the seeding phase. So for example, this could be an effect. And then some disease, like maybe some animals have more diseases, and then you have a lot of flips in the bases, and then maybe it would be more difficult to find the seeds, or also the extension might take longer because you have more errors, and then maybe the dynamic programming would run longer. But I don't have data, like empirical data, or like I don't have data to basically prove that this is, or like how much this varies now. I'm not sure, fortunately. Yeah. Then thanks for the attention. If there's no more questions. Okay, sure.
This is very cumbersome. So thanks. So they claim, the paper claims that they evaluate PIM, but it's really GenCache, right?
Yeah, it's this paper, GenCache, and they just take the values from their paper directly. So
okay. That's a big no-no in my book, but yeah.
Okay, yeah. To be fair, I'm not so what would you say is the problem with GenCache?
No, basically I think one of the difficulties in this paper is it's not clear where the bottlenecks are. I think people were also questioning that earlier. Like they claim it feels like a mishmash of different accelerators, and they take values from different accelerators in different ways. And They
Yeah.
claim one is memory bound and they do nothing about it.
Yeah.
So it's very odd to me.
Yeah.
At best.
I think it's yeah, transparent, and yeah, as you say that yeah, they use, for example, this the off-chip bandwidth has an effect, and then they use like quite a random ensemble of works to compare with. So yeah, those are also not the newest works at the time, and just one ASIC, and I think they could have maybe used compared with more ASICs, which would be like the closest to their work. So I think that's true. Yeah.
I don't know what to make of it as a result of this.
They achieved speed up, right? So at least for their configuration, it was not memory bound, but bound by their the scheduling and everything.
Maybe, but is it because of the baseline design is bad, right? I don't know. Maybe how does it compare to, for example, something near memory? There's a near memory accelerator does these things. So it's very hard to, I think, because the comparisons are not very apples to apples. To me. And you said, I think you pointed rightly some of the issues that you mentioned, right? Taking numbers from other papers, because other papers had some system configuration, which is different from their system configuration. It's very hard to match those numbers.
At least they show here that like their scheduler improves the baseline system, but yeah, it's also like a bit kind of obvious because the baseline is just the seeding units and extension units without anything on top of it, and that's the only thing, basically that they show that this is here an improvement here, but then I agree that like the baselines could be more systematic and more clear.
I can critique more, but maybe we can move to the next paper before we go into it.
I would like to see the reviews of this paper, kind of. But
I mean, I didn't read the paper in full right now, but it's a bit puzzling. Let me put it that way.
I
think the scheduling ideas are not new, right? They're using known scheduling ideas to really keep things utilized. So that kind of, I mean, that requires a much stronger evaluation methodology, which I don't necessarily see. So
if you don't have that much novelty on that side,
I think you pinpointed the issues nicely.
Thank you.
But one thing that would have been useful in this paper is really a breakdown of where the time is spent, right? In the baseline accelerator, plus their mechanisms.
Yes,
but that doesn't exist. I think.
Yes,
I mean, maybe it exists and you have read it, but
no, it's not there. Like you mean like on memory transactions and processing, like a breakdown of that?
Yeah, in general, yes, exactly. Where is the time spent in the baseline in different accelerators, ideally, but probably. Then they copy paste from other papers. That's not that interesting, probably.
Then they could have maybe shown like that it's actually memory bound and what the scheduler maybe probably doesn't really reduce the memory boundedness, but maybe a bit the computing bottleneck. But if the seeding isn't computing bottleneck to begin with, I don't know how much sense it makes. Even,
Okay. Thanks for the presentation.
Thanks. Okay.
Maybe a quick 5-minute break so that people can.
Release. Okay.
Okay. It's different. Okay. I've heard a lot of things.
Which one was the weirdest one?
I don't know. I don't want to remember.
Mine is so far con, which is not
Okay.
different, let's say, from the original. So maybe you want to wear this wire up. Yeah. Exactly like this.
Okay. Yeah, I think so.
We used to have hand actually microphones.
More?
Hand actually, the ones that are easier to carry. So I guess we don't have them anymore. Oh wow, this was actually.
No, I was telling you don't.
Okay. Okay, I guess we can get started. The second paper for today. So Elise will be presenting the second paper for today. I'll quickly introduce him. He's doing his bachelor's in the computer science department. He's in his fifth semester currently. He's interested in many related directions such as computer architecture, bioinformatics, designing hardware for AI as well, I assume. He's in fact actually working with us on a similar direction as well. So today he'll present this RawHash work, which is enabling fast and accurate real-time analysis of raw nanopore signals for large genomes. This paper was presented at ISMB last year. So please, Ulis.
Yeah, thanks for the introduction. So this is what I'll be presenting to you, and I'll get right started with the background. Why do we even do genomic sequencing and genome analysis? So one reason is to track diseases. This turned out to be quite useful during the COVID pandemic. And we can also perform evolutionary biology, study how species are related on the tree of life. Forensics and crime analysis, for example, understanding genetic variations, where diseases come from in populations. And ultimately, the goal here is, I think, to provide personalized medicine and gene therapy and make it accessible to everyone. So
The way we actually process genomes is this pipeline. You might remember that from last Thursday. So we start off with data preparation and sequencing. Then we process the signal in some way, and we do the alignment to a reference genome, and then we can perform all the analyses we'd like to make. So the actual hardware used for sequencing is varied. Here are a few examples. And I'll be focusing on Nanopore sequencing because it offers a few interesting trade-offs. So, for example, Nanopore sequencing supports long reads up to 2 megabases, and it's portable and low cost. So here you can see such a min-ion sequencer, and it fits into the palm of your hand. And data is also available in real time, which is a great advantage, as we'll see. This comes with a few sets of disadvantages as well. So most notably, these sequencers have lower accuracy compared to traditional technologies. And this causes the bioinformatics algorithms to be slower to correct for this lower accuracy. So let's dive a little bit deeper into how nanopore sequencing actually works. Here you can see such a nanopore in green, and there's a strand of DNA being threaded through the nanopore. So as it turns out, the DNA is negatively charged. So if we apply a voltage potential across the membrane, the DNA will actually, the strand will move through the nanopore. And when a set of K nucleotides is in the nanopore, is blocking the nanopore, this disrupts the flow of ions through the nanopore. And depending on the physical structure of the nucleotides, this generates a different unique signal. So this is how we can recognize what is being processed. As I said before, the data is also available in real time, and this actually allows us to give feedback to the sequencer. So for example, we can also abort a sequencing run. So just by inverting the voltage differential, this will actually eject the DNA because it is negatively charged, and so it will move back out of the nanopore. The advantage of this is that we reduce latency because we can overlap the processing time with the sequencing. And we can also reduce the overall time because we can actually sequence less and eject the DNA from the nanopore. So we save time and costs if we perform real-time analysis. The big question, of course, is how do we support this? And so if we go back here to the pipeline, and I'll focus on steps 2 and 3 here. This is a simplified view of the pipeline. So we have raw signal, which comes in the form of numbers, 1s and 0s. We then go through a process of base calling, which transforms the raw signal into a sequence of ACTGs. And then we do the alignment and mapping to our reference genome. So what's important here is that base calling is usually done using neural networks, and this is slow and complicated. And this actually increases the latency a lot. So the question is, how do we improve performance? Well, one possible approach is raw signal analysis. We can just go directly from raw signals to the answers we want. So what we want to do is compare the base called version to the raw signal. Of course, we cannot directly do this for alignment purposes. The main insight of the RawHash paper is that as the same DNA as it passes through the nanopore will produce similar but not exactly the same signal. So once we recognize this, we can hash both parts, the base called and the raw signal, and compare them this way. And the challenge, of course, is how do we implement this hash function to enable this? So here's the overview of the paper. The problem is that the pipeline is too slow due to the base calling. And we want to accelerate this by just working directly with the raw signal and enable real-time analysis. And specifically, existing tools that work on raw signals are too slow and not scalable for larger genomes. So the main contributions of the paper is a hash-based search mechanism for the alignment, and it enables real-time seed chain mapping, and the sequence until mechanism, which allows us to terminate the sequencing early once we've gathered enough information. The results show a significant improvement in throughput and higher accuracy for large genomes, but I'll go into more detail later on. So let's look at the actual methods, and I'll start with the hash-based search mechanism. So the pipeline starts by taking the base called reference genome. This is an online step called indexing, and we cut it up. And for each of these parts, we hash that and store the hash and its corresponding position in the reference genome into a hash table. Then when we're actually mapping the DNA in real time, we cut up the raw signal this time, hash that, and then we can look up these hashes in the table and obtain the potential alignment positions in the reference genome. Once we have this, we can plot this, and then the goal of chaining is to find a nice path through these potential matching positions and discard false positive matches. So here's the actual pipeline in its full detail. And you can recognize the two parts that I just mentioned, indexing and mapping here on the left and the right. And this might look a little complicated, but essentially the main parts are this translation layer in red that bring the different inputs, the base called reference and the raw signal, into the same input space for the hash function. And then they share, both parts of the pipeline share this hash function. And with this, we can then do the hash table query and the chaining. So let's start by looking at the sequence to event conversion in the indexing step. The way this works is that we take the base called reference genome and cut it up into overlapping k-mers. And for each of these k-mers, we then have a so-called k-mer model that has, for every k-mer, it has the expected raw electrical signal value. So while this k-mer passes through the nanopore, it generates a signal. And this table just records what the expected or average such electrical signal is. So we map every k-mer to this expectation. And then we standardize all of these values using a statistical standardization. So let's now skip over to the other side of the pipeline, to the mapping part. And before I can explain the signal to event conversion, I just need to explain the concept of events to you. So this is a sample output of a nanopore, so this raw signal. And we refer to such a thing in red as an event. So this is the segment in the raw signal that corresponds to one specific k-mer blocking the nanopore. So this we refer to as an event. So the signal to event conversion works by taking the raw signal and first splitting up the signal into events. So as you might have noticed, these events are usually characterized by a large spike. And this is because as the k-mer moves through the nanopore, when we change to the next k-mer, this is of course different, the flow is different, so we get a spike in the electrical signal. So we can use a statistical test to segment the signal. Then for every such event, we calculate an empirical mean, and hopefully this is the same or close enough to the mean recorded in the k-mer model. And then we perform, again, a normalization step. So now I'll go through the hash function, which is shared by both parts of the pipeline. So the first step is so-called quantization. And the underlying problem here is that the same DNA content can produce similar but not exactly the same signal. So we have some noise and we want to reduce this impact. And so here you see an illustration. We have one k-mer that produced similar but not exactly the same signal. So these are the corresponding mean values from the event. And here's a different k-mer that just produced a different value. So quantization just buckets these different values, reducing the accuracy of the values. And then we get, for all of these values that are close, we will get one representation that is unique to them. And for a different value that is further away, we will get a different value. So this is a bucketing approach. Then we perform the actual hash. So here another problem is that the k-mers are very small, so they will match very often in the reference genome, right? As a small k-mer can appear very frequently in a reference genome. So the idea here is to overlap several subsequent k-mers so that the longer the sequence we look at, the less likely it is that we'll find wrong matches in the reference genome. So we take the quantized values as just described, and then we take several subsequent ones and just pack them together into one value before we perform the hashing. Again, the goal here is to reduce false matches. So this is already the last step of the pipeline, the chaining. And so here I have an illustration prepared. So as you can see here, these are the reads of the raw signal and the different events. And for every event, we will get through the hash table many different matching positions. And what we actually want to find is a nice collinear set of positions that correspond to a mapping to the reference genome. So the way we do this is using a dynamic programming algorithm, and we reward matches and we penalize gaps. And maybe if you might have come across a similar concept in computer vision that's called the Huff transform, and this is sort of inspired by that. We just want to find this nice collinear set of matches. So I'll move on to the second contribution of the paper, which is the sequence until mechanism. And this mechanism works by continuously monitoring the signal, performing analysis. And then when we have gathered enough data, when the predictions have stabilized, we can then terminate the sequencing. So as an example that's mentioned in the paper, this is relative abundance estimation. So we want to estimate the ratio of a certain species in a sample. So we perform the sequencing on this sample, and sequence until will continuously monitor the ratio of a specific species in this total sample. And once the values do not change much anymore, we can be pretty confident that we've arrived to a close enough answer, and then we just stop the entire sequencing and save time. This was why real-time sequencing was so important to enable this. So here's a sample illustration. I just created this by taking a sequence with an underlying distribution and shuffling it and many times. And then I estimate for specific subsets of the sequence, for example, for 20%, 40, and so on, how close the estimation is after seeing only 20%, for example, to the original underlying distribution. So you see here, for example, at around 20%, we're already very close to the actual underlying distribution. So this is the mechanism that is used. So let me now go over the evaluation of the method. So 3 different workloads were tested in the paper. One is read mapping, and the ground truth here is a slow traditional base-called algorithm. Then relative abundance estimation that I just talked about. And finally, contamination analysis, where we want to detect the presence of certain species. And the data set consists of 5 different species that are supposed to represent different sizes of genomes. So we'll look at 4 different metrics. One is throughput, peak memory consumption, F1 score, and the evaluation of the sequence until mechanism. And the baseline here are 2 similar algorithms that also run on raw signals. So let's start with throughput. This is a large graph, so I'll explain this a bit. Here you can see the different workloads. So these are the 5 different species that we perform mapping on. Then we have the contamination analysis and the relative abundance estimation. And so these 3 bars correspond to the 3 different tools. And the numbers in here in white, they correspond to the relative speed up, so relative to the output rate of the sequencer. So this is here in gray. So the Nanopore sequencer emits around 450 bases per second. So if we want to be real time, we need to match at least this output rate. Otherwise, we're falling behind. And as you see here, for example, on larger genomes, such as the human genome, the SIGMAP tool actually does not manage to meet this real time requirement. I think the overall takeaway here is, first of all, on average, RawHash achieves a 25.8 and 3.4 x higher average throughput compared to the other two tools. And it meets all the real-time requirements. So it is always above this, this black line here. That was one of the goals. Next, I'll look at memory. So again, we have the different workloads and the different tools. This time, the numbers refer to memory consumption relative to RawHash. And notice the logarithmic scale here. So we can recognize that in general, RawHash has a moderate memory consumption. So just as a reference here, I inserted the 16 gigabyte memory line. So this is sort of just an arbitrary reference for maybe an edge device on which we might want to perform sequencing. And for most, but not all workloads, this is still a tractable method, RawHash. One of the methods uses less memory, or one significantly more. So takeaway, it is still tractable for most workloads, and the memory consumption is moderate. And in terms of F1 scores, as you know, F1 higher is better. So for most workloads, the tools show very similar F1 scores. And what I find particularly interesting is this bar here. So this shows that actually for larger genomes, RawHash performs better than the two other methods. And that was also one of the goals, to scale to larger genomes. And yeah, so compared to most methods, it's competitive, and there's a clear advantage for larger genomes. And then finally, the sequence until mechanism. I think this needs a little more explanation. So the way this was done is the data set was subsampled and shuffled, a bit like the graph I showed before. And then the comparison here in blue is a full run of RawHash of relative abundance estimation. And in purple here, you can see a run of RawHash that terminated after having seen only 7% of the data set. And the deltas here in the bars indicate the difference to a full run of RawHash. So what we can take away is that after having seen only 7%, so about a 15th of the entire data set, we can get very close approximations of the underlying abundance. And so it's an interesting property. So with very little data, we can make accurate predictions. Let me now move to strengths and weaknesses of the paper. So I think in general, it's the raw signal analysis is a promising approach, and there's many other groups and projects trying to make this work. And the sequence until mechanism is interesting because this is a new dimension along which to improve performance. So previously, it was just creating a fast algorithm that performs the mapping, but now it is also important to quickly give a result or a prediction so that we can actually sequence less instead of just align faster. Scalability is also pretty good, although there's a few caveats, and the performance, as we saw previously, is generally good. And finally, in terms of methodology, the paper is very clearly written. There were helpful illustrations, and there's also a well-documented open source implementation, which is always a nice thing to see. And for sequence until in particular, this is an interesting trade-off. When do we stop sequencing, and like how far do we continue to get maybe a bit more accurate predictions? And more importantly, this is not only applicable to abundance estimation, it's also not only applicable to RawHash, but can be used with other tools. So this is a separate component that can be used to improve performance of other methods. So this paper, of course, like anything else, always has weaknesses. So I think what's important is that to enable edge device processing, we really need to lower the memory requirements. And for some workloads, it is still too high and not tractable for portable devices. Then another problem is that event segmentation is not adaptive. So here I have this word homopolymer. So let me explain that a bit more. Imagine you just have a long sequence of the same nucleotides. So for example, a long sequence of just A's. Then as this sequence moves through the nanopore, this will not generate the spikes in the signal because it is always the same. Even as we move through the nanopore, the next k-mer is also just a set of A's. So this, the statistical test cannot recognize, and so this will lead to errors, of course. Then the k-mer model is static. So if we have noise that goes beyond what is provided in this static model, we cannot accurately model that. And there are other methods and algorithms that do not have this increase in complexity as the genome gets larger, the sequence gets longer. And then, quantization seemed a little arbitrary to me. So what I mean is that in the paper, there are only a certain set of bits of, so we have the mean electrical signal value. And the way we quantize is just to take a certain set of these bits, so a slice of the bits. And this corresponds to essentially taking a few bits of the exponent and of the mantissa of the floating point number. And it is also a linear bucketing. So we always have the same size of buckets because we always take the same size of bits. So that's another weakness. And then some more superficial weaknesses. In terms of metrics, the default parameters of the different tools are compared. So one might argue that the RawHash parameters were already optimized for these workloads, and maybe the other tools were not. And then there's also a specific set of nanopore chemistries missing, which was not supported in the paper. So we maybe do not have the full picture here. And then here, the min-no implementation. So min-no is a controller interface for the sequencer. So that would be good to have. And finally, in the paper, it would be nice if the actual hash function that is used could be described in a little bit more detail. So my takeaways from this paper, I think this is an interesting approach. It's fundamentally different to the existing pipeline that always first goes through this base calling step. And this is definitely something that should be investigated further. And this, as with any other methods, there's benefits and trade-offs of performing the raw signal analysis. And I think more work is needed to show this. And in general, genome sequencing can still benefit from many optimizations that can not only improve existing workloads, but might also unlock new workloads that we don't know yet. And I think my personal takeaway is to critically examine existing designs and really question if certain parts of long and complicated pipelines are really necessary. So before we go into the discussion, I'd like to just show you this quote. So this is by a French writer and aviator, Antoine de Saint-Exupéry, and he says, "It seems that perfection is attained not when there's nothing more to add, but when there's nothing more to remove." And I think this is an important lesson when we design systems as well, that it's always easy to add more hardware, to make algorithms more complicated, add features, and what's really hard is to remove stuff, make things simpler, and maybe in that way also make them better. So reducing things to their core idea. And with that, I'm happy to take your questions and discussion points. And I also have a few questions if you do not have any further points as well. So thanks a lot.
So I was wondering, as to like the performance, it seemed like aside from the fact that we could get reasonably accurate results with only a small subset of the data, it seemed like overall the performance was increase was pretty moderate compared. Like I think it was the uncalled algorithm or whatever that was. I think.
So are you talking about throughput here?
Yeah, because like the like it said the throughput wasn't much faster, wasn't substantially better, and uncalled has like substantially lower memory requirements. So is the main kind of improvement from this algorithm supposed to be from the fact that we can abort early, or were there more were these performance improvements of only like 50% relevant?
Mm-hmm. So this is like a full run. So we're not performing sequence until, and so maybe just a bit of details on the other algorithms. So uncalled uses something called an FMI index, borrows Wheeler transform. Maybe you've heard of that, but essentially here the problem is that when you get larger genomes, you'll get it's especially important in terms of accuracy. It's hard to match that. So this is an advantage of RawHash. So yes, this is what FMI indexes are interesting. They have sort of a constant memory usage, and the lookup depends on the length that you're looking for. And for SIGMAP, the reason why that is slower is that it uses a vector search, so that's more expensive. Does that sort of answer your question, or?
Yeah, pretty much. I mean, I think yeah.
Well, I'm happy to comment more if that wasn't.
Well, I just to totally clarify. So the advantage here primarily is that RawHash is constant, has a constant. No. Uncalled has constant memory usage, but RawHash can abort early.
No, sequence until, like, this is a separate contribution. Okay. So RawHash is just this hash-based mechanism. Yes.
Right, that's good.
Yeah.
So, yeah, I have a similar question. I have a similar question. So with sequence until, I think we didn't compare the other algorithms, right? Like
yes, that's
there
correct.
was the slide that showed at what percentage exactly, at what percentage what error do we achieve, and how would the algorithms compare there, or wouldn't that be very important to know?
I guess yes and no, but sequence until is sort of orthogonal. So RawHash is just this hash-based search mechanism, and depending on the algorithm that you use, that changes the performance characteristic. Sequence until will basically reduce the time. Like there is the latency generated by the alignment, and there's the actual sequencing time. So this can be used for all three of the tools.
Absolutely, and I guess it's probably linear, right? So if we only scan 5%, it's probably just 5% of the time.
You could assume that. Imagine,
yeah, but still, wouldn't it, like, how am I supposed to know? Like, is this a good result? So after, I don't know, 7% of scanning the gene, the error that we get, is this a good result? Because we don't compare it with the other algorithms, right?
Well, so here the metric is sort of to the ground truth, and not how much acceleration we get. Like
no, but I mean, if another algorithm would achieve at also, for example, 7% of scanning a lower error probability, then it's
okay.
That would be nice to know.
Yes, that could be a point. Yeah.
Hi. So from your presentation, it seemed like the hashing seemed like an integral part of the paper, right? But actually, I don't quite see the purpose of the hashing at all, especially if you go to the slide where you can see the hashing of the packed values. Through the quantization, you already have, before the hashing, values that kind of have the properties you want, right? They are in different buckets. And especially here, when you only pack 4 different values, it seems like it's even a smaller value. The only thing that I can think of why this hashing makes sense if you actually pack like hundreds of thousands of k-mers together. Is that the case? Do you know how many things are actually packed?
Yeah, thanks. So yeah, this is just for illustration purposes. I don't know exactly how many, but there's more than 4, of course. And so I think the problem is just that basically you do this on the indexing as well, right? The hashing is performed for both parts of the pipeline. So basically, if we'd have no packing, we would just hash for every individual k-mer. We would create a hash, and so this would appear very often, right? There'd be many potential positions where this k-mer can match.
But that's more about why we do packing, right?
Yes, correct.
But why do we do hashing?
To compare the different signals. So
they are different.
Let me
hash
skip
functions?
back to the.
Because I assume that we
So
use
this is the insight, right? We cannot directly compare raw signal to a base called sequence, but we want to align them. So we bring them to the same space by hashing to see where does the signal match in the reference genome.
Yeah, I totally get that.
Okay.
But the question is just because the hash function, obviously on the left and the right, are the same.
Mm-hmm.
So the inputs, like if the outputs are the same, then the inputs, or if the inputs are the same, the outputs have to be the same as well.
Yes.
So you could also just compare the packed values already right before you do the hashing.
Ah, okay. Oops, I'm going the wrong way. Sorry. Sorry for this skipping. So here.
Exactly. The value right before the hash box, basically.
Yep.
Because they should be the same on the left and right.
Well, first of all, you have advantages by the hash function because that distributes this, right? There might be patterns in here. These are floating bits of floating point numbers. So you distribute this across the space. And then secondly, I think you correctly said this before, we might get longer than the 32-bit number that the hash function produces here. So it's also reducing the length of this, which might be longer than 32 bits.
Yeah, I think if we actually pack a lot of these together, then the hashing does make sense. Thank you.
Maybe before that I can. So it's actually a very nice discussion so far. I want to address a couple of questions that we already had. One was about the 7%, whether this is basically comparable also when using other tools. So we actually evaluated that in the paper. It's in the supplementary. So what we did is first we used 100% in RawHash and showed that actually compared to other tools, RawHash was generating the most accurate results, and with even lower percentages. It was still more accurate than the other tools. So we have those results. But what we showed is that the sequence until mechanism is independent from RawHash. So you can take it and then apply it in other tools. It will still work given the, let's say, limitations of the tool itself. Second discussion was about why don't we pack more? So that's actually a good question. First, let's start with the assumption that we have the base code sequences and you don't have the, let's say, the raw signals. Even with that, you have a certain limitation. For example, if you take a 100-character long subsequence, you'll actually find very few matches in the reference genome. This is mainly because of, for example, the mutations that you'll get. So you'll miss many basically correct regions. So that's why there's actually a sweet spot. This is usually set based on some empirical analysis, and usually the sweet number over there is 20 character long subsequences. And there's basically a theoretical work behind it. Here in RawHash, if I remember correctly, what we packed is somewhere between 8 to 11 quantized values. So it is more or less corresponding to 10 to 13, 14 MERS. So this is slightly lower than 21 MERS. And this is simply because the raw signals are usually much more noisy. So if you were using base code sequences, then this means that you would be less noisy. You could increase your sequence length, and simply just because you're working on the more noisy data, maybe you need to just use a little bit smaller lengths. There was one more discussion. So I think this is about the scalability of uncalled for larger genomes. So there is one catch in uncalled, which is it uses a probabilistic model where it tries to guess, given a set of raw signals, what could be the set of corresponding, let's say, base code sequences. So there's basically a fixed size of sequences that you're checking at a time. So it is relatively independent from the genome size, but rather more dependent on basically what is your set size, which is determined basically, again, your the content of your genome. So that's why you're always working on the limited sets of sequences, and actually that's why its accuracy much lower than RawHash, because based on, so since you're not basically checking every possible region in the genome, you're very much likely that you're missing the correct region. So that's why it is a bit fixed. It's not basically dependent on the genome size, but rather the content and how repetitive it is, the genome itself. Okay, I think that's pretty much it, what I wanted to add. I hope some of the discussions were a bit clarified. Are there more questions about those? Okay.
So just to clarify, I mean, when we get like when there are even small errors, then when we hash the whole when we hash the thing, then the hash output is completely different. So do we for like the same sequences, or like when we're packing, do we basically have for the same, not pack, but for the same underlying truths, do we have several hash functions that, in order to account for errors, or how do we deal with that?
Yeah, so let me just see if I understood your question correctly. So you're saying if you get, for example, a flip in the base, then the hash won't match, and then we have a problem. Is this sort of?
Yeah, I mean, for example, if the average is just of like one of the events is just slightly off, then the whole hash in the end would be completely different. Yes. And you also said that like the input device you're using is not like completely is not that accurate. So yeah, how do we deal with that? Yeah, because as I said, like if there are small errors in the input, when we hash, we don't have the underlying truth anymore. So we cannot error correct like this, even the slightest error. So we have several hash outputs to compare with for the same sequences, or how do we deal with that?
So as far as I know, there's only one hash function. So errors that cannot be caught by quantization are either caught in the chaining, right? We might just have a part that we don't find, but then the whole chain could still be reconstructed. And then this is also, again, a trade-off sort of related to the previous question. If we have very long sequences and there's one error, then we won't find anything. So that's the trade-off between packing more values and less. So we could still find later on in the sequence and then still reconstruct the entire sequence. So yeah, as far as I know, there's only one hash function used in the paper, not multiple. Maybe, yeah.
Okay, and then we basically deal with it by quantization. So we the small errors are basically canceled out in the quantization. And yeah, okay.
Yeah, and if a base flips, for example, and we get a totally different measurement, then the rest of the alignments will still be correct and we can form a chain.
Yeah, okay.
Since you mentioned about one of the weaknesses you mentioned was that the quantization was not explained clearly, or that it was, well, you just chose to quantize certain bits from the data. Does that mean that for the different data sets, you'd that this would not work well enough and that you'd have to quantize some other bits for different data sets? Are there any other problems with RawHash where you have these parameters where, you know, it doesn't work for other data sets or other problems?
So so there's a slice taken from the signal value. That's the quantization in this version of RawHash, and this parameter was optimized across the different workloads, so it's sort of a trade-off again. But yes, you're right, we have this linear bucketing sort of, and actually RawHash 2, which is the subsequent version, sort of addresses this problem. And maybe again, in analogy to computer vision, there's different ways of quantizing, for example, an image as well. So what RawHash 2 does is a non-linear quantization. You might have values that are, let's say, more concentrated, and in that area you want more buckets. And then when you go further out, you maybe have like a less less dense distribution of values. So there you take larger buckets. So this is actually an improvement which was implemented in the successor of RawHash 2. Does that address your question?
Would this bucketing have to be done for every data set?
You mean like you need a different parameter for every data set? Is
different quantization schemes?
Yeah.
For different data sets.
So this is not done here. This could be an improvement, for example. Yeah. And yeah. Any other questions?
So probably you mentioned it already, but I didn't get it. So one of the weaknesses of this RawHash is the amount of memory that it uses. So I was wondering why it is so demanding in terms of memory with respect to the other methods like uncalled and the baseline, so the normal way to do it.
So maybe I'll just skip back again quickly to the memory consumption. Yeah, so as you can see here, so this tool SIGMAP here uses a vector search, so that explains why it is so much larger. This tool here, uncalled, uses an FMI index, which has sort of a constant memory overhead. And here with RawHash in blue, so this is mainly due to how the hash table is filled, right? If you have a larger genome, you'll have more different different k-mers, and so more hash values that are filled in your table. So this just increases your table size.
Okay, and when you were comparing the throughputs, and
yes,
you were showing the gray bar, that the nanopore.
Yes.
Does that method, so the standard nanopore, use less memory than RawHash, or is it comparable?
No, so this is the output rate of the device itself.
Okay, it's okay.
Yes, so this is like the rate at which signals produce, and this has to be matched by the different tools here in the colors.
Okay, I was confused by the two graphs.
Yeah,
one after the other. Okay.
Yeah, there's a lot of stuff going on. Yeah.
Okay. Thank you.
Okay, so I don't know if I have time for more discussion points, so let me move on to some points that I had prepared. So here are 3 points, and we can maybe look at them. The first point here is maybe like more general, moving away from RawHash, but also if you have RawHash specific ideas, maybe you have general comments on how to enable this on smaller devices using less memory. And you can also comment on any other of these questions as well. So in particular, I find this third point interesting to draw analogies. Maybe you have some ideas like in terms of machine learning or something, maybe one can take inspiration from there. So any inputs on that?
Since one of the problems with the hash function was that we cannot take arbitrarily long inputs because we will definitely get an error at some point and will not get the correct hash. Wouldn't another function instead of a hash function that kind of tries to deal with this by like doing exactly what a hash function is not supposed to do in mapping similar inputs to similar hash values, if you will? Like, is that a possibility at all? I have no clue if such a thing exists, but wouldn't it be much more reasonable?
So isn't that a hash function that you're describing? I'm not quite sure.
I mean, because the hash function, if you introduce one bit flip, the hash that comes out will be entirely different. So a function where, and for most hash function use cases, like what they are designed to do, this would be absolutely shitty. But in this case, wouldn't it be actually better if you introduce one bit flip, for example, the hash would be similar?
Yeah, I think that's a good idea. And also one point I had on the slides further on is maybe you could take the analogy of embeddings of an AI, right? You compare vectors. So this could be learned potentially, and that might be an interesting approach. The problem here is how do you enable this in a performant manner? How do you find close embeddings, for example, close vectors? And this would have to be, you'd have to be able to do this in an efficient manner to find nearby values.
Yeah,
but yeah, I think that's a good approach. Yeah.
You can also read the blank paper for that.
Nice.
Any other inspirations? Otherwise, I can talk a bit with what I came up with. So, for example, for this first point here, what could be, of course, interesting, that's sort of a standard approach, is implementing RawHash on accelerators. Maybe that's an interesting approach, and on PIM, this could be interesting. For example, if we distribute the data in an intelligent manner. Then, in terms of memory, so this can be directly addressed in RawHash, and some of this was addressed in the subsequent work, RawHash 2. So one idea is to do minimizer sketching. So that's like taking groups and just taking one representative hash. So we reduce the number of hash functions by taking many hash values and then taking one representative for this group. And another possibility, maybe to use Bloom filters in a way, we could compress the representation, or seeds that are not always the same, but we could look at different portions in a spaced manner. And then what could also be potentially done is to spend more time on the indexing, since this is an offline method, and perform some sort of a compression, maybe on the hash table, or compress the Bloom filters. Like, these are possibilities to reduce the memory footprint further. And so I think this discussion point is also pretty interesting, and there were a few comments about this before. How do we integrate methods? So, for example, this Kamer model, someone mentioned that. So one idea would maybe be similar to what was said before, different quantization techniques. We could also maybe fine-tune the Kamer model based on what we're sequencing. So this model is provided statically by the manufacturer. So maybe we would want to, first of all, measure on our specific machines if there's different variations that happen there in production, for example, and then also on different workloads. Maybe we could sequence only some of the sample, and then based on this, fine-tune the model. So this could potentially increase accuracy. What I also came up with is, for example, we could try running different algorithms in parallel. So maybe also different hash functions, this was mentioned, but also get the benefits of different raw signal analysis frameworks, or maybe running a more expensive step in the background. Like, these are all potential hybrid approaches that could be interesting. And then here, I think some of you mentioned this already, for example, this AI inspired approach, or I think also from computer vision, there might be a few interesting algorithms that could be an inspiration. So one classical way is to do banded dynamic programming. So instead of having the quadratic cost, we only calculate a certain band to save memory, and then we're sort of more in a linear regime. Another possibility, and there's been other groups at ETH exploring this. For example, here, a recent doctoral thesis that looked at A star search to have near linear time alignment. So maybe it is also possible to come up with new algorithms, and most approaches still use this classical dynamic programming, and this cost factor is really very important when you have large sequences, the quadratic cost. And then this was already mentioned, the embeddings to tolerate errors, maybe to learn and improve while we sequence, not just have a static policy, but we could also continuously adapt the neighbor search. And then finally, one of you mentioned this already, the quantization could be improved as well. So yeah, that's all I've got. Thanks a lot again.
Anything else to add, John? Nothing to add for the hashing discussion? Nothing else to add to the hashing discussion?